notes. 4.1b is motion. So if you guys noticed in homework, I think it stopped around the 40s. And once you get into like the 50s, it was word problems or motion problems. I kind of showed you on the answer key yesterday. But your notes are ready to go, roughly? 4.1 motion, we're going to do some review. Review? What? Where did we talk about motion? I want you to use your table of contents if you have your notebook from last semester. Where did we talk about motion the first time? Yeah, I was thinking chapter 2-ish. There you go. I want you to turn to that section, and I want you to find me the forever card that had all the motion stuff. Because when I say motion review, that's the forever card I'm talking about. When I say motion review, that's the forever card I'm talking about. Just take a second and look at that section notes. Now, some of you guys might not have written down much. Some of you guys might not have written much. For the problems, because you might have just been like showing the work, and so you didn't get the information, but there were word problems back then too, weren't there? And things were hitting the ground, or velocities were being found. Anyway, we're going to do some motion review, but first of all, you got to have a packet in front of you. Just really quick in context of you guys powwowing in your groups and about how some days are bad days, or sometimes you get in a funk, or sometimes you get back a bad quiz or a bad test, etc., etc. We still have Share the Hope cards. And so if you come across something inspirational, whether it's a verse, whether it's something your pastor says, whether it's like a quote, whether it's some picture on Insta, I don't know, something you're like, that's good. Remember, you can still share it. Okay, here we go. Motion packet. What'd you guys think? And maybe you didn't even realize it. Do you realize this whole thing was a big old blank? 3 closely related concepts in motion that you want to keep straight. We mentioned all 3 of them yesterday. Anybody? Ooh, I like time. All of them are in terms of time. So maybe let's say with time as the independent var, because everything's in terms of time, like Nick was just saying. The 3 closely related concepts in terms of or as a function or as functions of time. So time is important. What are the 3 functions though? Position, but why am I going to write that down here? Position, velocity, and acceleration. I should probably write it out since I did the other ones. Position could be in something like meters. Velocity could be in something like meters per second. And acceleration could be in something like meters per second squared. Right? Position, x of t, as an example. Velocity, v of t, as an example. Or dx dt, which is where you get your change in x, differential x, meters per change in time, differential time, seconds. Acceleration, a of t, could be written as dv dt. There's your change in velocity, meters per second, per time, per another second, so per second squared. Or you could also say the second derivative of position with respect to time, which is a little more awkward. I realize it's a little bit harder. But the second derivative of position with respect to time would still be meters per second squared. It's a little bit harder to see. But yeah, those are the 3. It's not working. There you go. Big concepts of calculus. And the notes that you guys just looked at, we were taking the derivative of position to get to velocity, derivative of velocity to get to acceleration. And what did I kind of reference yesterday? Now what are we doing? Going backwards. And the reason why is because there are many different models that have acceleration as a constant, like gravity. And we can go backwards from there. Initially, what do you guys think? Which of these variables, which of these quantities, time, acceleration, velocity, or position, should equal 0 if they say initially? Time. Now's the time to get the blanks right. You were trying, your groups were trying. Time has to equal 0 initially. Unless, I want you guys to put this, stated otherwise. What do I mean? If we're talking about like high tides or low tides, usually they say something like so many hours from midnight. And so there could be a situation that's starting at like 8 a.m. and it's the initial. In some ways, it's the initial. And yet, if you're midnight, it wouldn't be time equals 0. So usually initially means time equals 0. But every now and then, due to the context, it could be something a little different. At the origin, what do you think that's referring to? Time, position, velocity, or acceleration? Position, because it's where it is. At the origin. At the origin, at the beginning, but not just the beginning, at the origin, at the starting position. And specifically if it's talking about like something that's moving along an x-axis or something that's moving along a y-axis, at the origin is when x is 0, or even if it's y, when y is 0. But position is 0. At rest, actually acceleration, which is weird. You guys have a lot of experience with, in some senses, like you've driven it recently, right? Most of you this morning. Driven or ridden in it, but either way, you have things that you're somewhat accustomed to, like a speedometer shows you, like an accelerator pedal, which changes speeds, right? Like you have some relationship or some experience with this, which makes it easier, but you have some experience with this, which makes it harder. Like for instance, you're like, well, if you're at rest, your acceleration is 0, right? Sometimes. When could you be at rest? Acceleration is not 0. I want you to see how high this goes. Around there? What happened right there in this motion? It stopped. In between having a positive velocity, negative velocity, a speed up and a speed down, a positive number and a negative number, what had to happen in between by IVT? In between positives and negatives, there must be a 0, because this is a continuous function. It was at rest. What was acceleration the whole time? Approximately negative 32 feet per second squared. Why? Gravity. There was acceleration acting on it the whole time, but in between the change in position, here's another way of saying it. If you were going to the right, I would never advise you do this. Driving to the right with your foot on the accelerator pedal, still, I would never advise you do this, and do a sharp turn and change direction to the left. What's going to happen in between you going right and you going left? There's going to be a momentary stop. Very momentary. Split second in time. Stop. And there's some issues going on with your car and with people around you, and it's bad. But did you take your foot off the accelerator pedal? No. It's possible to have acceleration and be at rest, but usually not for long. Hey, I've kind of alluded to number 4. If the velocity of the particle is positive, velocity like a vector, velocity vector. I know, we're not getting crazy, but velocity like a vector has not only magnitude, Despicable Me, we're doing it in pre-cal right now, not only magnitude, but also direction. Like length, that would be magnitude. Not only magnitude, but also direction. Velocity has direction. So if velocity is positive, it is speed in what direction? You could say the right if it's a left-right model, but guess what? It could also be an up-down model. So right or up. If it's a left-right, a horizontal model, you're going to the right. If it's an up-down model, you're going up. And in this level of calculus, we're just dealing with one-dimensional motion, which means just strictly in one-line motion. So either right, left, or up, down. We're not going, technically, to be honest, we're not going up and to the right. We're not going to do two-dimensional motion because two-dimensional motion needs a position in terms of t horizontally and a position in terms of t vertically. Parametric functions. It needs x of t and y of t from last year. And the calculus is a little bit harder. That's a BC thing. We're just doing one-dimensional. So either you're going left-right or you're going up-down. How would you guys fill in number 5 then if it says moving to the left? Okay. First of all, put parentheses or down based on what we just said. But yeah, it is going to be negative. The sign of velocity. How about number 6 to find average velocity? Average. Ooh, average rate of change. Average velocity. Divide the change in position by the change in time. Change in position over change in time. And literally, if you want to write yourself a little note, even though we're going to try and get this in our notes as well. Change in position is a difference of positions, x of b minus x of a all over b minus a. Does that kind of ring a bell? F of b minus f of a all over b minus a, average rate. Instantaneous velocity is the velocity at a single instant in time. What do I want you to show for this one? X prime of t, or dx dt. Both of them have change in positions over change in time. Just one of them is as a result of the slope of a tangent line or a derivative. The other one is as a result of you doing it like a slope of a secant line over 2 points. If the acceleration is positive, increase. Did the increasing card help? A quantity is increasing when its derivative is positive, and whose derivative is acceleration? Just go back one. Velocity. Nice. If the acceleration is? I know, some of you just saw number 9 and were like, hey, I think it matches. Good critical thinking. In order for a particle to change direction from all that we've talked about, what do you guys think? What must change sign? Velocity. Is the sign of velocity is what tells you or indicates the right. And so from right to left, the sign changes of velocity, or the up to down, the sign changes. Okay, there's more in this packet. Holy cow, feel the packet, right? But right now, what's our goal? Letting you guys do homework from the book. So here we go. Section 4.1b, motion formulas. We have a lot. Let's start off with, since it's review, given x of t, given position. We can find, and if you want to, you can even label it, depends on how well you think you've got this from the motion packet. Because the motion packet is good, but that's not what you necessarily are studying for the test. Maybe you should. But that's not what, when the AP comes, you'll be looking back to. Does that make sense? Well, maybe you will. But either way. Let's get down the important stuff. We have x of t is position, and then v of t is equal to x prime of t, right? Velocity. If you want to put in units to remind yourself, that's totally fine as well. Some of you, it's just kind of second nature, so it's okay. Acceleration is equal to velocity's what derivative? First derivative. And position's what derivative? Second derivative. Good. That ran out of room. So how do we move? We need to take a ddt. And how do we move? A ddt. And that's the reason why we have a per second and another per second, which makes it per second squared. Really quick aside. Acceleration for, and we are going to call it free fall. Is a of t equals negative g. And I think you're going to see this in some of like the wordings of your problems. But it's going to come like before the problems. It's going to be like a section like you should have read the directions and you're not going to, and then you're like, I don't know what I'm doing. So let me help out. So acceleration is either going to equal negative 32 feet per second squared or negative 9.8 meters per second squared. This is precise enough according to basic physics. I haven't delved too deep into different things, like depending on where your location is on the Earth, your gravity technically does change a little bit. Because I don't think our Earth is a perfect sphere. But anyway, we're not dealing with that. And so as a result, let me see where I'm going with this. Yeah. Not only do we have our forever card that you guys already wrote down, but technically we could also say the following. Ready? We could also say that given acceleration is equal to a constant And we could call that constant a sub naught, which is the initial acceleration, but if it's constant, then it stays the same, so it's just one number. Let's say instead of last semester where we had to start with position and work our way forward, or start with velocity and work our way forward with derivatives, let's say if gravity is this thing that's at work, which it most definitely is, especially on free fall models, wouldn't it be helpful to go backwards? What would velocity equal if we were given acceleration? The integral. You guys know we can go backwards from derivatives with an integral, which means we would have the integral of a constant. Think of it like a k. How do you integrate a constant? Integral of k is kx or ky or kt. Haha. So it's going to be a sub naught t plus c. All right. Oh, stink. We're going to have a plus c and then a plus d and a plus or a c1 and a c2. Wait. What if you were given v of 0 is v naught? Guys, if you're given a clue about the function that you're finding, what do we do with clues if we have plus c's? Plug it in and then get the actual, right? So what if you were to plug in? What if you were to take this and be like, okay, v of 0 is equal to, hey, what's going to happen when you multiply a sub naught times 0? So guess what the constant's going to be? The initial velocity, which is why we can say, oh, hey, v of t for a free fall model is going to be a sub naught t plus v sub naught. So given a constant acceleration, which is only one way acceleration, you guys know if you're driving a car, your foot is changing on that pedal. It's not staying one speed. If it was, you're going to get in some big trouble real fast. But given a like gravity that's constantly working on something in motion that's falling, or rising and then falling, we can find velocity just based on a simple integral. And we can find position based on, you guys had a homework problem yesterday where you went from a second derivative backwards. Wouldn't we just take an integral again? So we're going to take the integral of velocity, which is the same thing as, all right, let's start plugging in. The integral of a sub naught t plus v sub naught dt. You guys know, take the integral of kx, or of a constant times x. Don't we have to do a power rule? So what would be the power rule if you have t to the 1? T squared over 2, which would be the same thing as 1/2 a sub naught t squared. Plus, how do we take the integral? Add an x, but in this case a t. Then don't we still need a plus c? Wait, but let's say that we're given an initial position, a starting position. What do we do when we're given clues? Plug it in, plug it in. So if we were to plug in, wouldn't we have x of 0 is equal to 1/2 a sub naught 0 squared plus v sub naught 0 plus c? Or I should say for a different time, like my whole hours from midnight example with the waves, high tides and the low tides, and then your initial time is like at 8. I guess technically you could start way back at midnight and then have t equal 8, whatever clue they give you. But every now and then you're plugging in when time is 0, so you'd actually have to solve. But if time is 0 is your clue, well, all of that's going to cancel out, and c is going to be the exact same thing as, well, let me go up. C is just going to be the initial position, which leads us to, for a free fall model with a constant acceleration, the position is equal to 1/2 a sub naught t squared plus v sub naught t plus x sub naught. Nick, this look at all like physics? Yep. Because in physics, they're just like, hey, these are a thing, memorize them. Cool. But there's a whole other type of motion. Let's memorize those. Oh. And there are all these relationships between our equations. Let's memorize those. But we're not a physics class, so we're not going to strictly just be like, hey, let's memorize all these things and hopefully know how to use them when the time comes. Our problems also aren't quite as hard as physics problems, but because we're more introducing the idea behind the physics, behind the formulas, or at least the math as to how it works. But for free fall, I want you to go find wherever I wrote that. For free fall, and I want you to highlight that because this isn't every single type of motion. This is just free fall when you're given a constant acceleration. For free fall models, where you're given a constant acceleration. And technically, constant acceleration doesn't have to be specifically free fall. That's just one of the most common. So maybe it might be a little bit more helpful if for this entire page, the point isn't so much the free falling. Hey, there's a song for that. But maybe the point, thank you, instead is the constant acceleration. No one busted out in song. Maybe it's too old for you guys. There we go. That's the one I was waiting for. I have musical people in here. Okay. The point is the constant acceleration. One example of that is free fall. Let's go check out some problems and see what you guys can do. So what if, remember, any word problem, well, what are you given? Draw a picture if possible. What are you supposed to find? And then solve. Oh, our seats changed. There you go. You were close, though, to your old one. What have you been given? Draw a picture. What are you supposed to find and solve? I'm debating the due date on the backboard. Do this every year with motion. Okay. As you guys are checking out, just the basic of word problemming. Word problemming? Yes, I just made that a verb. Okay, let's check out what we've got below. A vertical motion problem. I don't know, something's going up, down. Cool. A ball is thrown up with initial velocity, not thrown up as in at a curve, but literally thrown straight up. Remember, we're doing one-dimensional motion. With an initial velocity of 64 feet per second from an initial height of 80 feet. Hey, they're giving us like all those constant things. Hey guys, if a ball is thrown up and it's going to be coming down, what acceleration is acting on it? Starts with a G and ends with a gravity. And if this one says feet, we're going to be using that. I think it's in your homework in the directions. We're going to be using the equivalent of gravity in feet per second squared, negative 32. So how can we fill this in? There are lots of different ways. One way is just to memorize it. The other way is we technically could be like, oh, sweet, this is a straight up-down model, so I could start with negative 32 to find my velocity, which would be negative 32t plus c. But didn't we just talk about, wait a minute, if you plug in initial velocity, so v of 0 is equal to 64, don't we just get c to be 64? So we can say v of t is equal to negative 32t plus 64, which some people, if you look at that formula that we wrote down, you could have just plugged and chugged, put in gravity and put in initial velocity. Why is my initial velocity positive if my ball is going to be falling? Oh, wait, but it was pushed what direction first? Up, so positive velocity. It starts with a positive velocity, just gravity. The acceleration ultimately overtakes that and makes it come down. But actually, what they were asking for in letter A, position, so we had to go back twice. So you could go ahead and integrate the negative 32. Just because some of you seeing actual numbers to an actual example makes more sense where those formulas come from, so we're doing it once. But then you would have negative 32 t squared over 2 plus 64t plus c, which, here's the formula probably you can recognize, negative 16t squared plus 64t. Didn't we just talk about if they give us initial position, isn't that going to end up being your plus c? That wasn't too bad, was it? But what's the problem? Do we have more examples you think I want to do? Yes. Fine, homework due on Thursday, but start it tonight. Get out of here. Bye, guys. Start it tonight, but you're going to get stuck probably pretty early on. But start it first. Period 6 might get just a little bit further.